Okay, so this is part two in our series on deriving the C6H point group. And what we did in the first video is we were able to establish what the different classes were for this point group. And so we can now write a very large skeleton of our character table. And the reason why this is going to be so large is because we actually have 12 different operations, and each one of these is in its own class. So we have 12-dimensional space that we're dealing with here. So our first one that we usually write is identity. And then we have C6, we have our C3, and I'm dropping the hat notation here because these are classes, not operations like we were doing in the previous part one of this video. We have a C2, we have a C3-2. These are all derived from doing the C6 principal rotation axis multiple times. And they're all in separate classes in this case. A lot of times they wouldn't be, but in the CNH point groups or the CN point groups, this is how it works for reasons I explained in the other video. We have the inversion operation. We have S35, and the ordering of which you put these doesn't matter, right? I'm doing it sort of the standard way, but it doesn't matter, okay? You could put proper rotations up here. You could jumble these all around. That's totally arbitrary. S6 5 times. We have a sigma H in this molecule, as the H implies in C6H. We have an S6, and lastly, we have an S3. Okay, and so now we have a 12-dimensional space, 12 classes. So we're expecting to have a total of 12 vectors here. We should, that's what our character table rule says. And it's gonna take a lot of space if I write gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, all the way to gamma 12. And at this point, just to save space, I'm not gonna do that, but I'm just gonna write gamma 1. That's gonna be our irreducible representation, our first irreducible representation. We don't know what the Moltke symbol of these all are gonna be. I'll write a few, okay? But we know that the very first representation, or it's arbitrary which one's first, but in all character tables that people write it as the totally symmetric representation is the first one that they write. It's the easiest one to derive because you know it's always just going to be ones across the board. We have a 12-dimensional vector with ones at every component, and that's what it is. So one down, the easiest one. At this point, you want to start testing functions. And so I always like testing Z. So let's test Z for gamma 2. And so we're asking the question, what happens to the Z vector? Remember, the Z vector here is, we're defining a Cartesian coordinate system where your Z axis is where your principal rotation axis, your C6, in this case, your highest order N, goes along. Your X and Y can be defined however you want, but now we're asking, how does the Z function transform at C6H symmetry? So we imagine a Z vector, and we think about how does it transform with each of these, choosing one operation in each of these classes. Of course, there's only one operation in each of these classes in this case, so we only have one choice as we march along here. But for identity, we know identity takes anything to itself, so Z goes to Z. So there's going to be a one-dimensional vector that explains this transformation, and then we take the character or the trace across this matrix, which is a sum across its diagonal, and we can write, in this case, just a 1-by-1 matrix, so it's just 1. Chi, the character of the identity operation for the Z vector, is equal to 1, just the trace of this matrix. So we can put 1 here. And then we can march right along. So we do C6, and we get to the Z staying as Z as well. And the way you can think about that is you're doing a 60-degree rotation of the Z vector, but you're doing along the Z. So the Z vector is rotating, but it's just the arrowhead's still pointing up, which is really what it's defined as, right? And so Z just stayed to Z, it's still pointing up. And so I don't have to write this out again. Well, maybe I'll do one more time, but we're going to get the same thing, okay? And again, we take the character across the matrix, and chi of C6 is going to be equal to 1. And so now at this point, you can see, you know, basically if z goes to z, you're going to get 1. And for C3, C2, C32, C5, 6, all these are going to be the same. They're all going to be 1. And the reason for that is that you're just doing a different amount of rotation, but you're along the z. But because you're doing a rotation along the z and not by any other axes, your arrowhead's still going to be pointing up. What about our next one here, inversion? Well, inversion by definition takes any arbitrary point, x comma y comma z, and it takes it to negative x, negative y, negative z. And so here, z is very clearly going to negative z. And so now you're going to have your 1-by-1 matrix that describes this transformation mathematically as a -1. And you take the character of that, and it equals -1. So you're going to get a -1 because z went to the negative of itself. S35. Let's actually just skip over for a second and do sigma h, because the improper rotations are built off of sigma h. If you imagine a sigma h, that's a horizontal mirror plane. So that's going to be drawn by this blue plane in the xy plane. And so this z vector is above that plane. And so it's going to be seeing itself in this mirror and reflecting down. So it's going to go to the negative of itself. And so you're going to get z goes to negative z. And just like up here, when z went to negative z, we got a chi character of -1. That's what you're going to get for sigma h. Now, if we look at these different improper rotation axes, we know the definition of an S3 is just that it is a C3, in this case is S3 5 times, C3 5 times followed by sigma h 5 times. And we know that when we do a sigma h an odd number of times, that just equals to sigma h because we're flipping from top to bottom, top to bottom, top to bottom, top to bottom, top to bottom. It's the same as just going top to bottom, which is just one sigma h. So we know what C35 did. It did nothing to z, and sigma h did -1. So overall, you're just going to go z to negative z. And so you're going to get -1. An analogous thing for the other improper rotation axes, if you work through it, again, you're just going to get some rotation across the z followed by, that does nothing, followed by one mirror plane, which takes you negative to yourself. So the character is going to be -1. So what's nice about this is in this way, we rather quickly derived a new vector for this character table. And so what we want to do next is continue to test functions. And so after z, I always like to test x. Oftentimes x will transform in a much more complicated manner than z will, just because z, you know, is where the principal rotation axis is defined as. But let's do that. So we're going to test x. Okay, so we do an identity first operation here. X goes to x, nothing exciting. C6. All right, let's envision C6. We are now talking about an x vector, so let's draw that x vector here. And that C6 means a 60-degree rotation along the z-axis. So that's going to take you 60 degrees, somewhere in between x and y, 30 degrees away from y. And so x is going to transform as some linear combination of x and y. And we have to use our rotation function, which describes this here. And how it describes it is actually that the matrix xy transforms as cosine 2 pi over 6, negative sine, so it's 2 pi over n here, where n equals 6, negative sine 2 pi over 6, sine 2 pi over 6, and cosine 2 pi over 6. And so to get the character, we take the trace of this matrix, And we get that chi of C6 equals 2 cosine, and I'll simplify this as 2 pi over 6 as pi over 3. So pi over 3 is what? So pi over 3 is 180 degrees divided by 3. So it's a 60 degree rotation. So the cosine of that, if you think about your unit circle, is 1/2. And so that gives you 2 times 1/2, which gets you 2. So your character here is actually going to be equal to 2. I just did a very silly mistake. I said everything right out loud, but then I did the math incorrectly. So I said cosine of pi over 3 is 1/2. 2 times 1/2 is 1, not 2. So this value here has to be equal to 1, not 2. So let's just go ahead and change that. Sorry about that. So we have a 1 there. But what this tells us is that actually x goes into a linear combination of x and y, right? X goes into cosine pi over 3 or 2 pi over 6, cosine 2 pi over 6x minus sine 2 pi over 6y, and y goes into sine 2 pi over 6x plus cosine 2 pi over 6y. And so x and y depend upon one another. You can't explain x without also invoking y, and vice versa. And so back up here, we have to say, okay, identity takes y into y, and then actually consider the 2 by 2 matrix that does this transformation, the identity matrix, once across the diagonal. That's going to get you chi of, that's where my brain was with the 2, equals 1 plus 1 equals 2. So we have a 2 right there. And then we move right along. With the C3, you're going to get this same sort of matrix, but now instead of having 2 pi over 6, you're going to have 2 pi over 3. So chi of C3 equals 2 cosine 2 pi over 3. 2 pi over 3 is 120 degrees. And cosine of 120 degrees is negative 1/2. So you get a value of negative 1/2. You can move right along here. And this one, you could also use the cosine rotation formula if you want. There's nothing wrong with it. You're going to get cosine 2 pi over 2, which of course is 2 pi over 2 is just equal to pi. And that's going to get you negative 1. You could also think about this as, x is going to be spun into negative x, right? We're spinning 180 degrees here. That's usually how I like to do it. Y is going to be spinning into negative y. Y is going to be spinning into negative y. And again, I made a math error here. Cosine of pi is negative 1. So 2 times negative 1, we see a negative 2. But anyway, if you wanted to do it this way and visualize it, you get, this is for C2, right? X goes to negative x and y goes to negative y. And so the chi, the matrix that describes this transformation is negative 1, 0, 0, negative 1, right? X, y. Sorry about that negative there. And we would just take the trace across that matrix. And we would get negative 2, the same thing. Right? Negative 1 plus negative 1. So that's a negative 2 right up there. And then we keep marching right along. So our next one is a C3 twice. So it's going to be using our cosine formula that we have here. C3 twice. So that's going to be 2 cosine 4 pi over 3 now. Twice of the 2 pi over 3 one. 4 pi over 3 is 240 degrees. That's a negative 1/2. That's what the value ends up being. So that gives you a negative 1. So we got a negative 1 here. And then if we do the next one, which is C6 5 times, that's going to be 2 cosine 10 pi over 6, right? 5 times this, or 5 pi over 3. And cosine of 5 pi over 3, that's 300. That's 300 degrees. So that's equal to cosine of 300 degrees is equal to 1/2. And so that gets you 2 times 1/2 is equal to 1. Inversion. By definition, inversion takes x, y, z, any arbitrary point, and goes to minus x minus y, z. So inversion is going to look like just like C2. X is going to go to minus x, y is going to go to minus y, and you're going to get this 2 by 2 matrix with ones across the diagonals, negative ones up across the diagonals, and gets you going like that. So your chi of the inversion operator is going to be equal to -2. What about, how about let's do sigma h? It's useful to do sigma h first sometimes. Remember the sigma h, we have our vectors here. I'm just going to erase the dashed ones. And if we think about our mirror plane, horizontal mirror plane is perpendicular to the C6 principal rotation axis. X and Y are in that mirror plane. So they're both staying the same. Whenever you're in a mirror plane, you stay the same. So X goes to X, Y goes to Y, and you get the identity matrix. And you're going to get chi is equal to 2. So this is for the sigma h. Chi of sigma h equals 2. Okay, now we can do some of these other ones. We could do S3 5 times. Remember the definition of that, C3 5 times, followed by sigma h. Well, C3 5 times, C3 5 times. C3 5 times isn't going to do anything, right? Because we're just rotating along the z, just like all these other ones. So that's not going to do anything to x and y. Sorry, that's a z. That's not going to do anything to z. It is going to do something to x and y, right? And how is it going to do it? Well, we're going to have to use this sort of formula. So sigma h, though, doesn't do anything, as we just established. So sigma h doesn't do anything. So effectively, this is just equal to, for us, for x and y, is just equal to effectively C3 5 times. We actually haven't done C3 5 times. It's not one of these fundamental operations here. But what is C3 5 times equal to? C3 5 times is equal to a C3 twice, right? So sigma h doesn't do anything, C3 twice. It does do something. And how does it transform? It transforms as -1. And so from that, we can just say that the character is going to be the same as it was for C3 twice, which was -1. Sigma h didn't do anything. Our next one's S5 6 times. Well, S5 6 times is equal to C5 6 times, followed by a sigma h 5 times, which is just equal to sigma h, and a C5 6 times. C5 5 times is identity, spinning all the way around 360 degrees. So this is just equal to a C5 followed by sigma h. Sorry, I messed. I screwed this up. Not S5 6 times, S6 5 times. There's a difference there, right? Okay. Let's get back on track here. S6 5 times. S6 5 times, that's equal to a C6 5 times. There we go. Followed by sigma h 5 times, which is the odd number of sigma h's, such as sigma h. Sigma h, we know it doesn't do anything for x and y, right? That's what we're evaluating for. And so we just have to look up the character for C6 5, which we have right here is 1, or right there is 1. It's going to be the same thing. S6, C6 followed by sigma h. Sigma h doesn't do anything for x and y, so we just get the character for C6. It's 1. S3, it's the same deal. That's a C3 followed by sigma h. Sigma h doesn't do anything, so we just get the character for S3. So, we're getting closer here. We have successfully figured out at least the composite aggregate of x, y, and the reason why I'm saying the composite aggregate is because in a later, part of this video, you'll see that this actually vector has to break up into two subcomponents, and they're going to have some of these characters are going to be complex characters because there's no real functions that can transform as this symmetry and still be valid in terms of the rules of the character table. But we'll get to that. The next step from here is, we still need to get a lot more functions. We only have effectively 4 dimensions here. And we know we need to have 12 dimensions, right? We have 1 plus 1 plus 2, 4 dimensions. We need 8 more dimensions. So that's what we're going to work on in the next part of this derivation.